we, so for spin 1/2, we found that, that we worked for we found that there are these generators of angular momentum Jx, Jy, and Jz, and they satisfy the commutation relations. Okay, and we found all the properties of the spin 1/2 system. So for spin 1, we just posited that Jz was given by this matrix representation H bar 1, 0, 0, 0, 0, 0, 0, 0, minus 1. And that there are the same commutation relations. Okay. This was the only thing we really started off with, and then this is a spin angular momentum, and then we know from spin angular momentum from spin 1/2 case satisfies this, which is just the angular momentum commutation relations you expect for any angular momentum. So what we did at this point is we said we found that if Jz acting on lambda m gave us h bar m lambda m, and j squared lambda m was h bar squared lambda m, then if we define J plus minus operators that were Jx plus or minus I Jy, then we found we deduced from all of this here, we deduced then that J plus on Jm was equal to this C plus H bar, Jm and J minus, Jm is C minus H bar, Jm, where we found the C plus and C minus yesterday, where they were those kind of big messy things. Then from this, from J plus and J minus, we can construct Jx and Jy from just adding and subtracting. J plus is equal to Jx plus I Jy, and J minus is Jx minus I Jy. So J plus plus J minus. So if I add these, the Jy's will go away, and we'll get 2 Jx, and then J plus minus j minus would give us twice 2I jy. And since we found, so from j plus equals square root 2 h bar, and then we have a 1 here and a 1 here, and j minus, which is square root 2 h bar, what do we have? Let's see, the 1 here and the 1 here.
And how were those,
Isn't it the,
That's one here.
how were those matrices determined again?
By just, when we calculated the C pluses and C minuses.
Okay.
So then we can construct then Jx and Jy from these. We get Jx hat and Jy hat that we wrote down before. Okay, so this is just the logic that we went through, and I thought it was important to go through this again because this is general for any, any higher spin. You can do the same kind of thing, except it's a little more messy. But the procedure is basically the same. Okay, so this was for spin 1. Okay, now, so let's put this to use, but we're going to also recall that Sx hat was Jx and Sy was Jy and so on. We just defined those things as J's after we'd already found them. Okay, so Sy, for example, is equal to h bar over the square root of 2, and this was the one with the i's. So we have minus I0, 0, I0 minus I0, I0. Okay. So we have to, if we write a ket, in the z basis, we would write it like the following. It would be, some constant C1 times 1, 1 plus some constant C2 times 1, 0 plus some other constant C3 times 1 minus 1. Where remember this thing was 1, 0, 0 in the z basis. This ket was 0, 1, 0, and this ket was 0, 0, 1. Right, so this is all in the z basis. But now we have to, we want to be able to write it in the y basis, so So we need to calculate, for example, one in the y basis. So let this mean y basis. Okay? So this is like, in our previous, for spin 1/2, this is converting Z plus and Z minus to Y plus and Y minus.
Excuse me, Dr. Ju.
Yeah.
In your J minus matrix up there, it's missing an element.
Oh, this 0 up here?
Oh, it's 0.
Okay, so this is what we're doing now, but we're doing the same thing. We're going from a Z basis to a Y basis, but now our kets just have these different names, right? So everybody, are there any questions about that? Okay, so how do we do that? Well, to do this, and you can do this for all of the kets in the Y basis or the kets in the X basis. To do this, we'll write an equation in the Z basis. That will have these coefficients for the Y ket, or so that we'll be able to pick out the particular Y ket. So, okay, remember the JX and JY and JZ, they were all in the Z basis. So this operator is in the Z basis. Okay, so if you want, we could put a little Z up here to say it was in the Z basis. So if we know, for example, that in the Y basis, I can write this equation. S sub let's write S sub Y on 1, 1 in the Y basis is equal to, should be just be H bar times 1, 1 in the Y basis. So this is just a completely general equation because I haven't specified, I haven't written these things out in any basis yet. These are general, this is a general ket that expresses that we have the spin and, the top spin state for the Y ket, and then this operator isn't specified yet. But we can write the whole thing in the Z basis. Okay, so since this is in the Z basis, so we know Z basis of Y is equal to that thing, H over root 2. Then SY, if I write this in the Z basis, then this will be in the Z basis to make this be overly pedantic, when we choose to write SY, in the Z basis, then it only makes sense to write everything else in the Z basis to do the calculation. So let's go ahead and write that out. That's H bar over the square root of 2. And then we'll have our matrix here, 0 minus I, 0, I 0, minus I, 0, I 0. And then we don't know I don't know what column vector corresponds to 1, 1 on the Y basis. So here we just represent it as ABC. And we'll find ABC. This has to equal H bar A, B, C. Where A, B, C are to be determined. Okay? So let's go ahead and go through the exercise. We can drop the H bars. And so the top line, now if I'm just gonna do this matrix multiplication. So I'll have 1 over root 2 now. If I go across and down, I'll get minus IB, and then I'll have, in the second line, I'll have IA minus IC, and then in the bottom line, I'll have minus IB. And this has to equal A, B, C. Okay, so this gives us now the top, just equating these things, gives us the minus I over the square root 2b has to equal A. That's the top line. And then we'll have I over root 2 A minus C has to equal B. And then the bottom line is minus I over root 2b is equal to C. Oh, this is plus. Okay, that's better. Okay, well, so if I this line and this line together imply that AC is equal to minus A. And if C equals minus A, then this is equal to 2A, then we'll have root 2 times I A is equal to B. Okay, so that means that the ket so if the first element was A, C is equal to minus A, and then B is equal to I times the square root of 2 times A. Okay, so that's the ket. And now we want to just normalize it. So that means we'll take conjugate, which would be A star minus I square root 2 A star, and then minus A star, and then A I root 2 A minus A. And this would give us magnitude of A squared. This will give us plus 2 magnitude of A squared, and then plus magnitude of A squared. And we want this to be 1. So we have here 4 mag A squared equals 1. So take A to be 1/2. Okay, so then we can write finally that this, this ket is just equal to, 1/2, 1, I root 2 minus 1. Okay, so that's how you determine it. All right, so this means then that, so if we write 1, 1 in the z basis, that means this is 1/2 1 z plus I root 2. Well, it's 1/2, so this would be plus I over root 2 1 0 z minus 1/2 1 minus 1 z. Okay, just pulling that vector apart. So what this means is the following. This means for a Stern-Gerlach experiment, that if I have if I take a set of states that are polarized in this, in Y, in this particular ket, and I send these into an SGZ apparatus, then if I send N0 in here, I will get N0 over 4 here, N0 over 4 here, and N0 over 2 coming out. And that's just because those are the amplitudes of the amplitude squared, so will give us 1/4 here, 1/2 here, and 1/4 there. Okay, so now if you calculate let's see, 1 minus 1 in the z basis, you'll find this is 1/2 1. Let's see, I think it's just a plot. The minus 1 goes up here now. I root 2 and 1. Okay. So you can calculate all of the kets this way. You can calculate the x kets and the y kets, and it's a bit different than we did it for spin 1/2, but it's a lot faster to do it this way for spin 1. Okay, so there will be, there's homework problems on that, but just let me know if you have questions over it. So it's good to know how this procedure goes though, so. And this is a likely exam problem. Okay, that wraps up chapter 3. All right, so we're gonna start chapter 4 now. So before we start that, are there any questions before I continue? Okay, So we spent the last, the first 6 weeks now, doing just, some basic, working through the angular momentum and what states look like, what, we can write our cats out and change bases and all that kind of thing. But now we need to really solve problems that are of interest. You need to do the dynamics, so we need to understand time evolution of these state kits. So that's the start of chapter 4. This is time evolution of the state kit. Okay, so we're just going to, I mentioned earlier that when we have, when we had like the generator of rotations, we just wrote down an operator. That was an infinitesimal operator for rotations. So recall that the infinitesimal operator for rotations was given by, we did RZ, some d phi, and we said that was 1 over 1 minus I over h bar times the generator jz times d phi. All right, and then we compounded the things to find finite rotations and so on. So, and I said this was the form that we're going to use for all infinitesimal operators in quantum mechanics here for. So let's do a time evolution operator that is also an infinitesimal operator. So the operator for infinitesimal time translation is, we'll call it u of dt, and that will be 1 minus I over h bar times, now we're going to call this thing h, and then times this dt. Let's call it delta t. Delta t is small. Okay, so so h is the generator of time translation. Okay, and what is its effect when it operates on a ket? So what is the effect? So if we take u, this is hat on it properly here, of this delta t, it operates on a ket psi. Well, just by the definition here, what do we, if we have an infinitesimal time change, we don't expect the ket to change a lot. Right? It should stay pretty much the same. And that's what the 1 does for us. So we'll have 1 minus, since we need to write this out again, this will just give us psi minus I over h bar times h hat delta t psi. So this is a small change in the state ket. Okay, now expect that when we write this down and we talk about time evolution, we want to, ascribe a ket to be at a particular time, and then we want to look at that ket at later times. So let's go ahead and write this down as, we'll write down the same action so that you have this delta t on psi, and we'll say this is at t0, is equal to psi at t0 plus delta t. Okay, so that's just a statement that this time translation operator gives us the state ket at some forward time. Okay, and now we can go ahead and, if we compare these two sides here, this must be equal to everything here. So psi at t0 plus delta t should be psi at t0 minus I over h bar h hat delta t times psi at t0. Okay, so let's stop and look at the implications now that this equation implies. Okay, so we demand that psi remain normalized under time translation. Okay, and the reason is that if you don't, then the probabilities change. That means your probabilities might not add up to 1 if you do an experiment, and you can't have that. So we want them to remain normalized. So that means we can take this state ket and take its inner product with itself and see what we get. So let's do that. That will be psi at t0. Now, if I turn this whole thing around into a bra, I have to change the sign of this thing. And I also have to take a dagger here on my h hat. So I'll have this state ket, which just turns around. Then I'll have plus I over h bar, and then I'll have delta t is just a scalar quantity, so it comes out. And then I'll have h hat dagger. So I've got that operating then on psi t0 minus I over h bar h hat dt psi t0. Okay, so I'm taking the inner product of itself. And now let's work to order dt. So we'll say that dt squared is just 0. Right? That's just work the linear order of dt. So we'll have psi of t0 with itself. That will give us 1. And then we'll have, when these two operators hit each other, I'll have d delta t squared, so they won't contribute. So that's just 0. But I will have a contribution from this. So this will be plus I over h bar dt psi at t0 h plus. And then when this ket, or this, sorry, this bra hits this ket, I'll get a minus h hat. So this will have h plus here minus h psi at t0. Okay. Everybody follow that? So this all has to equal 1. So if I just cancel the 1 here and here, that means that if I'm demanding that this be the case, so that must mean that this is 0. So this implies that h hat dagger is equal to h hat, or h must be Hermitian. Okay, so that's an important thing that we just found. It says that the time evolution operator is also Hermitian. We talked earlier about when we had measurements, that measurements that gave real numbers out had to be represented by Hermitian operators. Okay, we just found that the time evolution operator is also Hermitian. Okay, so this is one important thing. Now the second one is to just look at this equation. So this is the same state kit here, t0 plus delta t. So if we take psi at t0 plus delta t, it's also equal to, I can just use this equation here. I can write it as u of delta t times that. So this is just psi at t0 times u hat dagger of delta t, u hat of delta t, psi at t0. Okay, and this has to be 1. And for that to be 1, we have to have must have that u hat dagger, u hat is equal to 1. So u hat is unitary. Okay. So u hat, the time evolution operator being unitary is one of the most important things in quantum mechanics. If it weren't, quantum mechanics just wouldn't work. Are there any questions?
So there's time evolution operator and there's a generator of time translation.
Correct.
Two different things.
Yes.
Wait, so, sorry. U hat is the, what you call that? Is that the time evolution operator?
It's the time evolution operator. H is the generator of the time translations. So H is, remember, so if we think about momentum, momentum is the generator of linear translations.
Yeah.
And angular momentum is the generator of rotations.
Right.
And H is the generator of time translation.
Okay.
So there's a physical quantity that will be associated with H.
And when you say time translation, you just mean like
Time
evolution past,
Yeah.
just time going on?
Yes.
Okay.
Is that, would that be arbitrary sometimes? Like if time is unknown, like, or if we know that time passes, I guess, but if we don't know how much has passed?
I mean, there is, it's a really, that's kind of a deep question, you know? How much time has actually passed? How do you even really know that? for
Yeah.
sure? Right, I mean, if time slowed down, all of our measurements would slow down, and, all that kind of stuff, right?
Mhm.
So, all we know is that time moves forward, it doesn't go back at all.
Right.
So, in a very real sense, you could reparameterize time to move twice as fast, or
Mhm.
move half as fast. But as long as it doesn't turn back on itself, it doesn't, you would never know.
So like, I just know like, so our spin operators we had were Hermitian, right? The J's,
The J's,
right?
yeah.
And our rotation operators were unitary, right?
Yes.
Yeah, so is there any, like, so we also have a Hermitian and another unitary that you're showing, like, is there any connection between that?
Yeah, I mean, that's why it's all the same idea, right?
Mm.
You have a generator that generates either the translation or the rotation.
Then you have a differential you're adding to it.
Okay.
That's just to make sure it's a very small change. It's generating very small pieces, and they're add up over time to a big change.
Yes.
Well, I was saying is like, so if you took those equations that you did and you substituted H hat for J hat and d phi for dt, it'd be like a very similar equation. That's how you prove it for the rotation, right? Or is it?
Yeah, I mean, it would be, it's basically the same, except instead of time, you have something else.
Okay, yeah, that's what I was saying.
Yeah, it's all the same. Okay, other questions? Okay, so remember we compounded for a finite rotation. We compounded many infinitesimal rotations. We do the same here. For finite time translation. So let t be, dt over n times n. Oh, sorry, t over n times n. And dt is equal to t over n. Then u hat of the time, the finite time t will be the limit as n goes to infinity of 1 minus I over h bar h hat, and then delta t, well, that's right, delta t to the n. Okay, and so this is just e to the minus I over h bar h hat times t.
Are we gonna talk about phases now?
Not yet.
Not yet.
Okay, so that's the time evolution operator in quantum mechanics. And now, let's finally get around to a differential equation. So we want to make a differential equation out of, you know, if out of basically, you know, this equation. So let's go ahead and write our time evolution operator acting on a state kit. But let's first just consider, first let's consider this all in here. If I take u of t plus dt, I'm going to try to make a derivative out of this thing, minus u of t over delta t. Okay. This should be like the derivative of u. But now u is just I compound these infinitesimal time translations in order to get a finite one. So I can just write this thing. This I can write as u at t, and then u hat delta t, because I'm just compounding a finite rotation by another, finite rotation by an infinitesimal rotation, so it's just this, it's just this. And now I'm subtracting u hat of t over dt. Okay, now we can, so for a finite rotation, we have just this expression, so this I can write as 1, well, first of all, let's write it as u hat of dt minus 1 times u hat t over delta t. Then if I just take this stuff in the parentheses here and I subtract the 1 off, I'll have minus I over h bar h hat dt acting on u hat of t. And I divide out dt, which I can cancel. So du of t, this is du hat dt. And it's just u hat dt is minus I over h bar h hat u hat of t. Also, no, you can get it very simply by just differentiating the exponential, but it's useful to see that kind of manipulation. Okay, so let's let it act now on a state kit. Okay, so it's just some state ket psi. And if we take d by dt u hat of t, and let it act on psi at time 0, this has to be equal to minus I over h bar h hat u hat t acting on psi at some time t0. but this is psi of t, and this is psi of t. So we have the time rate of change. We have IH bar times the time rate of change is equal to H hat psi of t. So I just brought up the H bar and then I multiplied both sides by I. So that tells you that the generator of time translation when it acts on a ket just gives you the time derivative of the ket. And this is Schrodinger's equation. Okay, so we'll solve this in many different situations here, but this is the equation. This is what we were kind of getting at since the beginning when I mentioned that you're not interested in the position of a particle or anything like that. You're interested in the evolution of the state ket with time. So particle trajectory doesn't really mean anything here. It's just what's meaningful here is what are the amplitudes as a function of time in the state ket. Okay, let's see. All right, so now let's think about what H represents. Okay, so what does H represent? Physically. So for this, we'll just consider, let's consider psi at some time t and relate this to let's just call it time 0. Okay. So this equation, we have psi hat t, h hat psi t. If we write this in terms of the ket at time 0, this is u hat dagger t, h hat, u hat t psi 0. Right? Okay, now there's a really important thing that we have to. So u hat of t we found was e to the minus I over h bar h hat t. Okay, and this thing has an expansion just like any exponential. So this is 1 minus I over h bar h hat t plus 1 over 2 factorial, all that stuff, minus I over h bar h hat t squared plus 1 over 3 factorial cubed plus dot dot dot. So what I want to use the property that u dagger u is 1. So that means I want to scoot u dagger to the right, or I want to scoot u dagger u to the left, or I want to move h past u. You can say it a million ways. And in order for that to happen, I have to know what the commutation relation is. What is h I mean, does H commute with, the time evolution operator? So what's your feeling?
Oh, yes,
Why?
because how else would we solve it? I mean, it would be really anticlimactic if you said no, and that's the end of that.
Good, yeah, okay. Well, but what makes you think it should? This isn't a problem.
Can we get back to the definition of commute real quick?
Well, I mean, the first thing I noticed is that, you know, H dagger is equal to H, but I don't know if that has to do anything.
Does an operator commute with itself?
Yeah,
So why then would H commute with,
because U contains H and only H.
Right.
Okay.
so
That's,
it's just powers of H?
yeah, that's what my thought.
I
My
see.
thought was like, wait, well, we don't really know what H is in this scenario. And that's like, yeah, that's where I got stuck. So that makes sense. If U contains H, it must be.
So it contains H. So these things, I mean, it only contains H, so it will just commute with itself. You know, because if I took something like H with H squared, this is just H cubed minus H cubed. Right, so it'll always commute. So that means I can just move the U over here, and then we'll use U dagger U equals 1. So U hat dagger H hat U is equal to U hat dagger U H. And this is just 1. So that means that this, we can call this the expectation value of H at time t. And that has to equal this, which is the expectation value of H at time 0. So if this is a quantity that just doesn't change when the system evolves, what do we call it?
Constant.
It's a constant, yeah. What, did somebody else say something?
It's conserved.
It's conserved, it is. So if it's not angular momentum or momentum, what else is there that's conserved when in a system?
Energy.
Right, it's the energy. Okay, so H is the Hamiltonian of the system. Okay. All right, good. Now, so we have a new operator. So what should we do?
Use it.
Define it.
Operate.
Well, we already did, it's the energy.
Okay. operate on a system, I guess. Find a system that it applies to.
Okay, but what did we do with all of our other operators? What did we do with our angular momentum operators?
Use them on a state kit.
Yeah, to do what?
Not
To
transform it.
rotate it or.
So move it.
Well, when we defined the z projection of the angular momentum, what did we define what kind of relations were we writing down? I mean, what did we want to do, especially when we went to spin one?
Projections on the other axis.
Finding the algebra was my thought, but that's not it either.
Well, that's one of the important things, but what did we do for JZ, for example, you know, in the spin one system, or the spin one half system?
Find out how many states.
Yeah, okay, but to do what? We wanted to do what? What did we do?
Well, find the total. We can find the total,
find
because like
how many
J squared is the
states
total
there are.
angular momentum. Like, so you're finding like the total energy of the system.
Yeah, but, we wanted to find all of the states that were meaningful for the JZ operator, right? And J squared.
You mean like the cyclic sort of thing that we do? It's like went from this height to
Oh, so
Whether it has a
you wanna find all
maximum
the energy
value or
states
not.
with this, you wanna find all the energy states
Right,
of a,
exactly. We want to find all of the energy states of the system.
Oh,
So it's called finding the spectrum of the operator.
are you using the ladder operators again?
In certain cases you can, but
Okay.
not in all cases. But yeah, we'll get to that when we get to those things. So we want to find the spectrum of the operator. And that's just another way of saying we want to find all of the eigenfits and eigenvalues. Okay, so that's a problem that we're going to come to. But before we actually write down a physical problem and solve for the spectrum, let's just assume that we have a spectrum, and then let's see what let's see what happens when we operate on it with the time evolution operator. Okay, so we want to find a set, a basis set, and this will be in the energy eigenvalue basis. And it's denoted by phi sub n, where n is in either a finite or infinite set.
Oh, so this is like, so you're saying we send it through the magnetic field and we see how it splits?
Yeah.
Okay.
That's exactly right, yeah. So I mean, so we you know, the basis kits that we used for spin 1/2 are in fact also energy eigenstates. But this might be some other system that doesn't have like a magnetic field or anything. It's gonna be like, you know, a particle in a box or something. That's what we do later. But, so these the basis set, I mean, you know, when we do anything like so for spins, you know, we have these spin states and they're all discrete and they're finite and pretty easy to deal with. You know, when you talk about for an actual particle, like that's confined to a box or something, the basis states, there's an infinite number of basis states, and you know, it just gets a little bit more. A little harder to deal with if you're doing computations, for example. Okay, so if we have such a set, and we have the set of eigenvalue equations, where En is the eigenvalue of energy corresponding to the ket phi n. Okay, so this is our eigenvalue equation.
So it's gonna be operator, the state, the ket equals some number, ket again.
Yeah, eigenvalue equations are,
It's always gonna be that format.
yeah, it's very
I know
well.
I'm saying the
yeah,
obvious, but I'm just trying to.
because you know, in linear algebra, what do? This is exactly what you do. You try to find. You want to find eigenvectors and eigenvalues. So, okay, so now so how does what does the time evolution operator do to an energy eigenstate? So this is a big important thing. So we want to operate u hat t on phi n. Okay, so what do I do? I mean, what is it? Let's write out let's write the evolution operator. This is e to the minus I over h bar h hat t acting on phi n. So what happens? We talked about this before, so. Remember, if you have an operator and an exponent, and the ket is an eigenvector of that operator, what can we do?
Don't you just have your eigenvalues replace the h in
Exactly.
the expansion?
So then what does that give us over there?
Well, all the rest of them would disappear, and aren't you just left with the first term?
No,
No?
I mean, all the h's do, you're right, they all turn to ENs. So what does the expansion give you then?
The sum of all energies, of all possible energy states.
No, because there's only one ket there, phi n.
Oh, I see.
Every time h operates, it gives you En. So you're right, I mean,
It'd just be that expansion.
it's the expansion with h replaced by e sub n. So what,
Right, okay.
how do I write that then?
As a sum.
It's e to the,
I want to write it as the next, I want to write it as the
yeah,
expansion.
replace the h, hat with
Should
e.
replace that with the, yeah.
Right, okay.
Everybody remember that?
I do.
Yeah.
As long as this ket is an eigenket of this operator, then you can just replace it with the eigenvalue. Because you can just do the expansion, and then, you know, so this is just En t.
You really gotta understand, you're trying to teach us quantum mechanics and it's almost 5 p.m. Like, brains are not firing on all cylinders right now.
We'll just go with that.
Like like, I don't know, Dr. Gibb had an observation this morning, it's.
So we use we use our statement up here,
I'm using this, yeah,
right, to get to this other.
in this
right,
expansion,
Right,
because every time an H hits it, it just gives me back another E.
and say, okay, we know these are eigenvalues for this operator.
Yeah.
We see that the operator's in the exponential, and so we can, because we're referencing back to the expansion, we can say, oh, let's just swap these. And
Yeah, I mean, you can think of it, I mean, you don't have to work it out, you can just, you can expand it, you know all these turn to E's, and then you can just recompress it back into the exponential. So so that means that means the phi n of t sorry, E n phi n. Okay, so let's do, let's do a quick example here. Let's consider a two-state system with H equal to 2 and a quarter or something like that. Okay, and let's call phi 1 1 0 and phi 2 is 0 1, so that H hat on phi 1 is equal to 2 phi 1. So this is E1, and H hat on phi 2 is equal to a quarter phi 2, so that's E2. So if we had psi at time 0 was equal to C1 phi 1 plus C2 phi 2, then psi at time t would be C1 e to the minus I over h bar times the eigenvalue for that, 2t phi 1 plus C2 e to the minus I over h bar 1/4 t phi 2. Okay? So now what you'll notice here is that these terms, the magnitude of this exponential, anytime you have an exponential with an I in it, the magnitude of it is always 1. But it's, this is a cosine and a sine if you write it out. So there's oscillation in the amplitudes because of the changing the changing of the phase up here, and so that gives you all sorts of interesting interference issues within the way, if you have more complicated. This is really simple because there's.
So depending on your time evolution, like the time evolution operator, that's what H is, or
Yes. Well, H is the
time
that's
step
the generator.
of the generator. Yeah. So depending on your generator, the different states wobble at different rates over time.
Yeah.
Yeah.
Good way
So
to
like,
put it.
the phi is the circle, right? Yeah, the circle slash third. I was like, because you said phi and psi.
Phi.
Yeah. Okay. So like phi 1 would be oscillating faster because it's 2t
Right.
compared to the psi 2, which is quarter t.